Okay, this is a third video segment that I'm doing on the concept of isostatic restraint in Catia, which is related to the 1, 2, 3 rule in dynamics, or self-balancing forces in Catia again. The first one, I took a block, which this particular one is continuation of what I already did, and it was not completed quite, so I'm going to add a second part to that particular video. Okay. The problem that I did earlier, the very first tutorial on this business of isostatic, was actually a block like that, but there was a hole. There was a hole in the middle, and what we wanted to do is to develop or find the stresses in this particular problem. I'm ignoring the hole, and the block has dimension 1 by 1 by 1 here. Okay, this particular problem is what is called a self-balancing load. In other words, this entire structure can be in the back of a truck, and the truck moving, but this is still in equilibrium, although it's moving. So what the key was in Catia, or at least the 1, 2, 3 rule, is to apply three constraints. For example, at the point A, restrain the translation in 3 direction, at the point B in 2 direction like that, and the point C, which is up here, in 1 direction. This takes away rigid body motion, and if you look at the reaction forces and the stresses at the points A, B, and C, you'll see that there's 0. Okay, so this is the case of a self-balancing load. Okay, the only things that these restraints do is to make sure it doesn't move as a rigid body. Now in Catia, well, if you look at this problem now, this is almost the same one as before, except that there is no force loading, or there's no pressure loading to the right. Okay, so this is a non-self-balancing balancing load, and I'm going to solve this problem for you and look at what happened at the point A, B, and C all the way on the top there. And in Catia, if you want to do this problem, instead of you applying these restraints, what you can do is you can go and apply isostatic restraint on the part, but this will be this has 2 options really. One is the self-balancing, and the other one is non-that. Right now, the way it looks like, it's non-self-balancing. Now, if you ask Catia to do it as a self-balancing problem, then internally Catia applies a force on the right-hand side, okay, or somewhere. Okay, so to know exactly where it applies it, one should look at the documentation of the FEA program. It could be applied, for example, at the center of mass of this object. Then this is going to be an isostatic loading or restraint, which is asked by us to be self-balancing also. So I'm going to do this problem. Let me see now. Okay, this is not what I want. We'll do a second problem later on. So let's go ahead and in Catia and start with a part file. All right, first let's make a 1 by 1 by 1 block. So on this plane, I'm going to sketch, and I'm going to make it nice and symmetric because I'll have some plans later on. Let me see. This is 1 inch. This is 1 inch. This is 1 inch. Exit, and this is padded by also 1 inch. So it's the block we're talking about. All right, let's apply some material property to this. Let's apply, for example, the steel. to this part. Okay. And now we're going to go to generative structure analysis, mesh this thing. Okay, that's fine. And we apply a pressure of 100 pound on this side, or psi, 100 psi on this side, and it's tensile, as you can see. Okay, now obviously, if I run this thing, it will bomb out. Let's try it. Let's try it. So here, you can see it's going to be moving as a rigid body. Not necessarily translating, but it's a rigid body motion in space. Obviously, it's not just strength. Fine. Okay. Let's deactivate this plot. All right. Now, of course, I can go and do that 1, 2, 3 rule, 1, 2, 3 rule myself, but this is not the self, as you can see, this is not the self-balancing load. For example, let's try it. If I apply the three restraints here, okay, and on this top point, I will make it. Let's see. Right. This is good. Okay. And finally, so this actually it may be easier if I did it instead of that vertex. Let me cancel that. Down here it's easier to see what's going on. So this vertex does not move in the direction y. It's free to move in direction y because of the Poisson ratio effect. This can be, of course, be shrinking. And finally, at that one point, we prevent motion to avoid rotation there. This will work. This is the 1, 2, 3 rule. It will. Let's run it. Okay, it will work. And if you want to look at the stresses, for example, here, let me reset my scale here to the default, right there, and let's change the rendering, and there we are. Okay, but look at what happened at these corner points. At these corner points, because of the restraints that you put in there, all of this load that was on the left side, that left face, is going to be transferred into these reaction forces, and we get something that's useless. Okay, so let's go ahead. First of all, let me go ahead and delete these restraints. Delete this, delete that. All right, now let me do the same thing, except that instead of me doing the 1, 2, 3 rule, use the isostatic restraint. You click on it, and now you're going to run it. Notice there are no restraint. All I did was to say isostatic restraint, and I'm going to run it. Guess what? You get the same kind of behavior. Okay? Right there. Now, see that? This point and this point this time. So this is an example of a non-balancing load where the loads are actually all transferred into the artificial restraints that we put in there. Okay, now obviously, if I put a load here with a pressure of 100 psi tensile and run it, everything is going to be great. But let me show you something here. If you double click on the load here, see that on this load line. Never mind the pressure, load. double click on it, this dialog box opens up, and here is a box which says self-balancing. Check it, and then you want to say, is it self-balancing or is it not? If you say yes, internally what happens, it applies a pressure, or it applies a force equivalent to the magnitude of the force imposed by this pressure in the opposite direction. And of course, now we have isostatic. It should not be an issue. It's going to run, and you're going to get no reaction forces or stresses, artificial stresses at those restraints. Restraints internally that are put by the isostatic group. There, you see that? You see? The other thing is, you notice is that it makes sense because you apply the pressure of 100 psi here, okay, and this end there is a counteracting force internally generated, okay, and then there are these restraints here. These restraints will actually prevent the rigid body motion of this. So basically, there is no stress here, okay. All right. So that's what that self-balancing restraint does. Now, look, if I go and say, do not take that into account, of course, I'm going to go back to the original situation. So if I go back to the load and say, no, I don't want any self-balancing mechanism, so we run it. Of course, all the forces are going to get transferred to the restraints, and of course, they're going to be right there. See that? Unrealistic things put on there. Now, just a word of caution, if you're using restraints, if you're using symmetry restraints, one has to be careful. In this particular problem, it doesn't matter, it will work. So let me see actually where I am. Let me go ahead to my model. And let's see now, in the part body, I'm going to take half of this model due to symmetry. So actually 1/4 of it, that's what I mean. So cut it with this plane. Cancel that. Let's try it again. Okay, try it again. Cut it with this plane. Oh, not mirror. I'm sorry. Undo. I want to cut it, split it. I don't want to mirror it. So where is the split? Cut it with this plane. Keep the other side. Or keep the other side. It really doesn't matter. Okay. And cut it with this plane. Okay, so this is 1/4 of the model. Let's go back to our analysis. Okay, the pressure is still on that face. That's fine. Now restraint, we have additional restraint here. These are surface sliders. So let me see now. There's a surface slider, and the bottom is a surface slider. Okay, let me do the other one. It really doesn't matter, but this one and that one. Okay, and now run it. This was self-balancing, remember? Okay, so activate. Was it self-balancing? I don't know. Maybe not. Or maybe I put it back. So let's go back to load. Oh, yes. I want it to be self-balancing. Run it. And activate the plot. Okay. Okay, I have a problem here. Let me make sure that my restraint. So this is okay. Let me do something else. Here. Deactivate or delete. Okay, so let me go ahead and change my restraint This I'm going to delete. Okay, and the pressure, the load, self-balancing, yes. Okay, good. And I'm going to put isostatic on this part, and let me run it again. What I was trying to do is to show you that when you're using planes of symmetry, you really have to be careful, because this business of self-balancing self-balances may or may not work. So as a matter of fact, let me change this. Let me deactivate that. And let me take the pressure on the other side. Okay, let's see how that thing works. Because I have a feeling I know what is going on. If you look at this, if you say if you go to the isostatic, right-click and restraint on visualization on mesh, you see that? What happened is that the restraints that are automatically put on this model is at this end, okay? And therefore I want the pressure to be at the other end. So let's do the following. Let's okay. Let me deactivate that. Something is also showing here. Mesh is showing. Deactivate that, and take this pressure, put it on the other side. Not on this side, on that side. Because I cannot move that restraints that Catia puts there automatically do isostatic one. And this is why I'm saying, if you're using planar symmetry, be careful. There may be some issues, you have to sort it out. I just moved my load. This is self-balancing, okay, so you should be getting, oh, where did it put? So it put the constraints here. That's going to be tough, because the bottom line, this could have worked depending on how I created the model, but as you can see, it didn't. There's another reason. Let's see. Yeah, my guess is that one of those restraints is at this point. Okay. In fact, if you go here and say, show me this thing, right there, you can see that. You see this? One of the traits here. So when you're using planes of symmetry, be careful. It may or may not work. All right, so let me close this. Close that. Go to the second problem that I would like to do. So it's a thick-walled pipe. Think about a pressure vessel, thick-walled. Okay, there are no thin-walled approximations, and we have inside radius 1, or sorry, inside radius 0.5, outside radius 1, and load of pressure of 100 internally applied to this thing. And if you stick these things into the theoretical formula, you should get around 167 psi. Let's go do this problem. We go here, start with the part file. Let's go make this thing. So on a convenient plane, on that horizontal plane, I will sketch 2 circles. This is going to be the hole, basically, inside radius 0.5, diameter 1, and another circle inside radius 1 for diameter 2. Exit, add it. Let's make it 2 inches. Okay, good. And let's apply material to it. Metal, steel on the part. All right. And we go to Catia. Mesh this. Okay, yeah, that's fine. I'll use that. And let's see now. We will apply pressure here on that inside face, 100 psi, so that it pushes into the sidewall. Right there, you can see this. All right, good. Now, obviously, if I run this thing, it will run into issues because this is free to move as a rigid body. Okay, so let's run it and see what happens. It's going to bomb out, and you can see that it moves as a rigid body like this. Okay, so deactivate this last spot. Right here. Deactivate this. All right. Now, let us apply isostatic restraint here. Isostatic restraint on this part. Now, notice that this particular problem is already self-balancing because if you look at the loading, it's already self-balancing. So when I run it, it should be working fine. In the previous problem, when I had a block, when I did not activate self-balancing option, it did not look right. Okay, but let's run it here. This will work without actually saying it is self-balancing. Okay, let's look at the von Mises stress, for example. And let me change my scale to 1 because it was changed for the previous case. All right. And change the rendering. Material shading. Now you might say, wait a minute, didn't we apply 100? Yes, but this is von Mises stress. So if you really want to see what the stress is, you should be looking at the principal stress, namely your hoop stress. So let's plot the hoop stress, or actually let's do the principal stresses, and double click on it, and go and select, first of all, average ISO, and then select only C1, which is C1 is the largest one, which is the hoop. Okay, well, this is not very good, so let me change the rendering here to, or let me change the type of element to parabolic and run it again, or change the size of the element. Actually, you know what? Let's go ahead and change the size here. 0.05. Run it. I kept the element type the same, but made it finer mesh. Let's look at the principal stress. Okay, see, actually these numbers are not changing that much. Okay, and but at least there is no weird pattern here. So what I'm going to do is I'm going to change this thing to self-balancing, yes, and run it. Let's look at it now. 174. Oh yeah, of course, look. I don't know why I did all of this, because here's what the exact solution should be. 167. For some reason I thought that the pressure that I applied was 100. Okay, the pressure that I applied was, but the hoop stress is theory says 167. This is 174. Now, if you want to see the radial stress, so plot the C. Let's do plus C2. Actually, C3 probably is what you want. The smallest, the Yeah, the intermediate. Well, let's see now. This is a PSI. Let me see for a second. Something not working here. Radial stress is C22. Okay, so it should be 100 here, and it should go to 0. Why is this thing so small? This doesn't look right. So let me check a couple of things. Principal stress component, that is fine. What? I'm sure that my load was okay, and this was self-balancing. Let's check that one more time. Self-balancing, yeah, yes. And I don't like the fact that principal stress tensor component. Let's see now. Let's try this. Oh yeah. All right, right there. This was principal shearing that I didn't apply. This is principal value. Okay, fine. And this is principal tensor component. Something doesn't look right. Well, this is okay, but principal stress component, that is fine. C1 is okay. C2, yeah, that's good. Yeah, C2 is what I want, right there. Here, the red stuff is 100 psi. This is what I applied. Remember, I applied 100. Of course, it drops down to 0 radially, and this is why it's going to blue. So look, moral of the story is this. By the way, this is the one that I just generated for you. Moral of the story is that, well, first of all, for that problem that I did, look at where these internal constraints are applied, but that is the thing that I would like you to be aware of. Be very careful. If some planes of symmetry are used, isostatic constraint may not be leading to the correct answer, whether it's self-balancing or not. I did not use any plane of symmetry. Always use isostatic constraint with caution. All right, folks? Take care.